Good morning, students. Uh, Today's in this video, we are going to learn IDFT, that is inverse discrete Fourier transform by using FFT algorithms. Okay, so IDFT using FFT algorithms. So we can perform inverse discrete Fourier transform by using FFT algorithm, either decimation in time algorithm or decimation in frequency algorithm. You can use any one, okay, with the help of the same algorithm, same logic. So the FFT algorithms, which can be used to compute an inverse DFT without any change in the algorithm. So the inverse discrete Fourier transform of a endpoint sequence that is given by x of k. So where the k is existing between 0, 1 and so on up to n minus 1, and it is defined as x of n which is equal to 1 by n sigma k is equal to 0 to n minus 1 x of k and the twiddle factor w minus nk. So this is the formula for inverse discrete Fourier transform, IDFT. Okay, IDFT of x of n. So where this w is nothing but a twiddle factor. So which is nothing but w is equal to e to the power of minus j 2 pi by n. Okay, so this is inverse discrete Fourier transform formula. Now how can we calculate IDFT by using FFT algorithms? Okay, so first of all, take a complex conjugate of and multiply by n, so that we obtain n into complex conjugate of x of n, so x conjugate of n. Okay, so which is equal to sigma k is equal to 0 to n minus 1 x conjugate of k. So we are taking conjugate, so x conjugate of k, and w twiddle factor w n k. Okay, so we are taking complex conjugate now. So what happens here? So this minus can be turned into positive. Okay, so take this is one of the important step. Take complex conjugate and multiply by n. Okay, so afterwards what happens here? The right side, the right hand side there. This means this one, the right hand side, this portion. Okay, so is a DFT of the given sequence x conjugate of k, and may be computed by using any one of the algorithm. Either we can follow DIT, that is decimation in time algorithm, or the decimation in frequency algorithm, whatever it may be. So the desired output sequence x of n can be obtained, which can be found by complex conjugate the DFT and dividing by n to give the x of n value. Okay, so initially what should we do here? So first of all, we defined x of n. Okay, but in order to compute IDFT, inverse discrete Fourier transform, okay, we should take the complex conjugate. We should take the complex conjugate of x of n. Okay, so complex conjugate of x of n and multiply by capital N. Multiply by capital N. Okay, so this is the step one. This is step one. Okay, so n into x conjugate of n is equal to sigma k is equal to 0 to n minus 1 x conjugate of k w and k. After that, this becomes the right side and the right hand side of the equation, which is nothing but the DFT sequence of x conjugate of k, the DFT sequence of x conjugate of k. And now by using any FFT algorithm, either decimation in time or decimation in frequency algorithm, okay, the desired output sequence. Okay, so the desired output sequence x of n, okay, which is obtained again by taking conjugate of this equation, that is the right side of this equation, and divided by this 1 by n. Okay, so that the x of n can become again once again 1 by n, 1 by n. Okay, sigma k is equal to 0 to n minus 1, sigma k is equal to 0 to n minus 1, x conjugate of k, x conjugate of k, twiddle factor w n k, okay, whole over the conjugate. So this is x of n. So like that way, so we are performing idft by using FFT algorithm. Okay, it can be explained by taking one example so that you can easily understood. Okay, so here I'm taking one example. Compute or perform idft, okay, of a given sequence, of the given sequence by using decimation in time algorithm, DIT algorithm. And my x of k sequence, it is given by 8 0 0 0 and 0 0 0. How many number of bits? 8 bits. Okay, so this is my x of k sequence. Okay, so I need to verify, I need to found the x of n value. Okay, so students, so here what is asking, perform idf to the given sequence by using a DIT algorithm, decimation in time algorithm. Okay, so here I'm giving here he given the x of k sequence is given that 8 0 0 0 0 0 0. Okay, so observe carefully. So again we need to follow the same DIT algorithm steps. Okay, DIT algorithm steps. What is the step one? Just step one. The number of samples. The number of samples are given by n is equal to 2 to the power of m. Okay. So here the number of samples are nothing but 8, and which is can be expressed in terms of 2 to the power of m. So this is 2 cube. 8 can be expressed in terms of 2 powers. So 2 cube, which is equal to 2 power m. So where m is equal to 3. So the total number of stages are obtained, that is 3 only. Okay, step 2. Step 2 is nothing but so the input sequence is shuffled and which follows a bit reversal order. Okay, so bit reversal order, which follows bit reversal order. Okay, so here x of k, what is the x of k? What is bit reversal order? We should follow the bit reversal order. So here what should we do here? Instead of taking the sequence 0 1 2 3 like that, we should consider bit reversal order. Okay, and step 3. What is step 3? We need to form the how many number of stages. Okay, so the number of stages which is given by the number of stages, which is given by m is equal to log n to the base 2. Okay, so we know the value of capital N, that is given by 8, so that's why the number of stages are obtained, m is equal to 3. Once again we are define this. Okay, and next for step 4, what is step 4? So in each stage consisting of n by 2 butterflies, so each stage consisting of n by 2 butterflies. Okay, that means so total number of stages are 3. So for each and every stage, it is consisting of total number of butterflies, 4 butterflies. Okay, and the next step, fifth one. So input output are separated by the, so input and outputs for each butterfly, which are separated, which are separated by uh, by 2 to the power of m minus 1 samples, where a small m refers to stage index. Okay, so for first stage, okay, input outputs are separated by 1 minus 1, that is equal to 2 power 0, that is 1 sample. That means input and outputs of butterflies are separated by only 1 sample. Okay, for second stage, so input outputs are separated by 2 power 1, that is 2 samples. Okay, for third stage, for third stage. So 2 power 3 minus 1, that is equal to 2 square, that is 4 7. That means here input outputs of for each butterfly separated by in stage 1 1 sample, and in stage 2 it's separated by 2 samples, in stage 3 it's separated by 4 samples. Okay, that is steps 5. Okay, and step 6. What is step 6? Step 6 is nothing but the number of complex multiplications. Number of complex multiplications which are given by n by 2 log n to the base 2. Okay, so we know that the value of n, so 8 by 2 log 8 to the base 2. That is 4 into 3, which is equal to 12. Okay, so that is step 6. And step 7. In step 7, the number of complex additions which are obtained by using the formula n log n to the base 2. Okay, so we know that value of n, again by substitute the values and we get number of complex additions, that is 2. So 8 into 3 and finally its value is equal to 24. That is step 7. And step 8. What is this step 8? The number of sets or sections. Okay, so the number of sets or sections of butterfly in each stage, which is given by, okay, so the number of sets or sections of butterfly in each stage is given by 2 to the power of m minus m. Okay, so here we know that the total number of stages are 3, and stage index are given by, okay, so stage index are given by stage 1, stage 2, stage 3. Okay, so 1 2 3. So here if m is equal to 3 and small m is equal to 1, and the number of sets are given by 2 to the power of 3 minus 1, that is equal to 2 square, that is 4 sets are occurs in stage 1. Okay, so m is equal to 3 and small m is equal to 2. The number of sets or sections in stage 2, that is obtained 2 to the power of 3 minus 2, that is 2 power 1, that is 2. Okay, the number of sets m is equal to 3 and m is equal to small index, stage index is 3. So the total number of sets or sections of each butterflies in stage 3, which is given by 2 power 0, that is only 1. So here the 4 to 1 refers to the number of sets or sections of butterfly in each and every stage. Okay, that is step 8. And here the exponential repeat factor ERF. Okay, so it is also obtained by using the same formula 2 to the power of m minus m. Okay, and stage 1 already we know that the total number of stages are 3. Okay, so stage 1 the small m value is equal to 1. So the exponential repeat factor is 2 power 3 power minus 1, that is 2 square, that is 4. So here in stage 1 the exponential, that fiddle factor which is repeated by 4 times. In stage 2 m is equal to 2 and 2 power 3 minus 2, that is equal to 2 power 1, that is equal to 2. In stage 2 the twiddle factor which are repeated by 2 times. In stage 3 m is equal to 3. Okay, so 2 power 3 minus 3, which is equal to 2 power 0, that is equal to 1. So in stage 3 the twiddle factors which are repeated by only one time only. Okay, so that is a step 9. Now we will see the most important step, that is twiddle factor. Twiddle factor. Okay, so this is the most important step. Okay, the twiddle factor which can be find by using stage index, that is given by k is equal to nt by 2 to the power of m, where the t which is nothing but 0 1 2 and so on up to 2 to the power of m minus 1 minus 1. So we need to find the twiddle factor for each and every stage. Okay, so here in stage 1, okay, so we need to find the value of t first. In stage 1 the stage index value is 1, so the t value is 2 power 1 minus 1 minus 1, that is equal to 2 power 0 minus 1, that is equal to 1 minus 1, that is equal to 0. That means it has t value only 0. Okay, so if m is 1, t is 0, what about k? K is nothing but n into what is the value of 0? 0, and 2 to the power of n. So obviously the value of k is 0. Okay, so in stage 1, m value 1, t value 0, and what is the value of k? K value is also 0. Okay, now we will see the stage 2. In stage 2, so again in stage 2, the stage index value is 2, and the t factor, its value is equal to 2 power 2 minus 1 minus 1, that is equal to 2 power 1 minus 1, that is equal to 2 minus 1, which is equal to 1. So we need to consider up to 1. So we need to consider 0 and 1. This is important. Okay, so this is very, very important. So we need to consider up to 1. So already we know that if m is equal to 2, if m is equal to 2 and t is equal to 0, so we obtain the k is equal to 0. If m is equal to 2 and t is equal to 1 and k is equal to, that is nt by 2 to the power of m. So here the value of n 8 and this is t value 1 and 2 to the power of 2. So if it is m index as well 2, so 2 square, and we need up to 8 by 4, that is 2. The k value is 2. Okay, and this one. Now in stage 3, the value m is equal to 3, value m is equal to 3, and the t value, that is we need to consider up to that value. So m minus 1 minus 1, that is equal to 2 power 3 minus 1 minus 1, that is equal to 2 square minus 1, that is equal to 4 minus 1, that is equal to 3. That means we need to consider up to 3. So 0, 1, 2, 3. Okay, so here for m is equal to 3, m is equal to 3, t is equal to 0. So obviously the value of k is equal to 0. Okay, if m is equal to 3, t is equal to 1. Okay, now see k is equal to nt by 2 to the power of m. Okay, so here n is equal to t and t value is 1 and 2 to the power of, here m value is 3, so 2 power 3. So here 8 by 8, which is cancelled, so 8 gets cancelled, the value of k is equal to 1. Similarly, if m is equal to 3 and t equal to 1, so if m is equal to 3 and t equal to 2, and we obtain the value of k is equal to 8 into 2 by 2 cube, that is equal to 2 only. This 8 gets cancelled. Similarly, if m is equal to 3 and t is equal to 3, okay, so the value of k is equal to 8 by 3 by 2 cube, that is equal to 3. Okay, so in stage 3 it has 4 total factor values. Those are k is equal to 0, 1, 2, 3. Okay, so after finishing the algorithm, now we need to find out the twiddle factors. Okay, so what is the formula for twiddle factor? Twiddle factor formula is nothing but w n k. Okay, which is nothing but e to the power of minus j 2 pi k by n. Okay, so here our number of points 8, n value is equal to 8. So w 8, when k is equal to 0, okay, so this becomes 0 and we obtain e to the power of 0, that is 1. Okay, and w8 whole to the power of 1, w8 to the power of 1, that is equal to e to the power of minus j 2 pi. What is the value of k? K value by 1, so k value into 1 by 8, that is equal to e to the power of minus j pi by 4, which is nothing but cos pi by 4 minus j sin pi by 4. The value of cos pi is 0.707 minus j 0.707. Okay, so this is nothing but cos pi by 4 minus j sin pi by 4. Okay, similarly w8 to the power 2, that is equal to e to the power of minus j 2 pi into by 8, that is equal to e to the power of minus j pi by 2, that is equal to cos pi by 2 minus j sin pi by 2, and which value equal to minus j. Okay, and finally w8 whole 3, that is equal to e to the power of minus j 2 pi by 8 into 3, that is equal to e to the power of minus j 3 pi by 4, and we know that cos 3 pi by 4 minus j sin 3 pi by 4, and its value is equal to its value is obtained. So minus 0.707 minus j into 707. Okay, so there are four twiddle factors are obtained. What are they? So one is minus j, and another one is this one, and this one, and this one. Okay, so we obtained 4 twiddle factors. So again, how can we perform this discrimination in time algorithm? Okay, so once again I'm explaining here DIT algorithm, the butterfly how it's going to work. Okay, so here two parameters are there, A and B. Okay, and the twiddle factor which is exists at B, so W8 some K. Okay, so the formula for this twiddle factor is A plus B into W8 into K. Okay, this is A minus B into W8K. That means the twiddle factor first should be multiplied with B. Okay, and this product one time it is added with A, so that's the final. It is at resided top side, and one time it is subtracted. The product is subtracted from A, so that is A minus B into W8K. Okay, so now based on these rules, now we would like to find. We would like to find what is that idft by using DIT algorithm. idft by using DIT algorithm. Okay, so now we will see. So the flow graph butterfly diagram. So here this is input and it is output. Okay, so you should remember in idft we should take complex conjugate of x of n. Okay, that means we should consider we should take x conjugate of k. Okay, but we don't take the x of k. Okay, so here according to the step 2 in DIT algorithm, we should write the input side, okay, bit reversal order. Okay, now see, after writing the bit reversal order, so we need to take x conjugate of 0 and x conjugate of 4, x conjugate of 2, and x conjugate of 6, x conjugate of 1, so x conjugate of capital X conjugate of 5, and x conjugate of 3, and x conjugate of 7. So we know that sequence. So here all our x of k sequence is consisting of all real values only. So there is no imaginary terms. So there is no problem at all. If any imaginary terms are there, we should change the sign. Okay, so why? Because we are performing conjugate. So here what is x of 0? X of 0 is 8, and x conjugate of 0 is also 8 only. Okay, so 8. Similarly, remaining all samples. So that is a very interesting thing here, that I am considering the x of k sequence is consisting of only real terms only. So there is no modification. If x of k is the sequence which is consisting of any imaginary terms are there, so after performing conjugate, okay, so if any imaginary terms are there or complex terms are there, their signs are changed, gets changes. Okay, so you need to consider those sign conversions at the time of especially um, if any image terms are there. Okay, so here x conjugate of 4 is 0, so this one is 0, and this one is 0, and this one is 0, and this is 0, and this is 0, and this is 0. Okay, so now I am draw the stage 1, stage 1, stage 1. So this is my stage 1. So according to the step 5, in stage 1, input outputs are separated by one sample only. Okay, so here input outputs are sampled by one sample only. So one sample only. Okay, and the twiddle factor in stage 1, that is equal to W8 whole to the power of 0, that is its value is equal to 1. Okay, W8 whole to the power of 0 and W8 to the power of 0, W8 0. Okay, so here how can we perform? As I explained, okay, this one in which is multiplied with 0, this one is multiplied with 0. So this value, the product value which is added with this 0 one time and again subtracted with one time. Okay, so here 8 plus 0, so 1 into 0 0, so 8 plus 0 8. Okay, 8 minus 0 8, and 0 remaining all zeros, so 0 plus 0 0, 0 minus 0 0. Okay, 0 again 0 again 0 0. So stage 1 is completed. Okay, now stage 2. Now stage 2. So in stage 2, according to the step 5, the input output separated by two samples. Okay, so the graph is like this way. Input output separated by two samples only. Okay, so this is like this way. Okay, so this is and the twiddle factor, that is W8 power 0, it is now 1, and this is W8 to 2, that is equal to what is the value? This is pi by 2, so its value is equal to minus j. So again, this is W8 power 0, so W8 to 2. So here the exponential repeat factor is 2. Again the same thing. So the twiddle factor which is multiplied with this value. So here in this case, this 1 is multiplied with 0 and it is added with this 8 one time and subtracted with 8 from subtracted from 8 one time. So here 8 plus 0, that is equal to 8, and 8 minus 0, that is equal to 8. Similarly for this one. Okay, so minus j which is multiplied with 0, that is 0. Okay, so one time it is added with this 8, so 8 plus 0 8, 8 minus 0 8. So here 0 and 0 and 0 0. Why? Because 0 plus 0 0 and 0 minus 0 0, and this one. Okay, and this is stage 2 is completed. Now we will see stage 3, the final stage. Final stage is 8. Okay, so in stage 3, so according to the step 5, input output sample separated by 4 samples. Okay, so 4 samples. So here the flow graph is, the input is separated by 4 samples, that is okay, and this point is separated by this one, and this point is separated by, connected to this one, and this is connected to this one. Okay, and this is connected to this one, this is connected to this one, this is connected to this one, and this is connected to this one. Okay, so the twiddle factors, so W8 out 0 and W8 1 and W8 2 and W8 3. Okay, already we know that W8 value is equal to 1, and W8 to the 1 is, that is nothing but 0.707 minus j into 0.707. W82 is equal to minus j. W83 is equal to minus 0.707 minus of j into 0.707. Okay, again by applying the same formula, this twiddle factor which is multiplied with this 0. Okay, so it's 0, so it is one time it is added with this 8 and subtracted with 8. So what is the value here? So here we get this is 8 here. Okay, it is 8 plus 0 8, and 8 minus 0 8. Similarly this 8 plus 0 8, and this 8, and 8 plus 0 8, and this is 8, and this is 8, and this is 8. So all are which are nothing but, these are nothing but n which are nothing but, these values are, this is nothing but n x conjugate, a small x conjugate of 0, and this is n small x conjugate of 1, and this is n x conjugate of 2, and this is n x conjugate of 3, and this value n is equal to x conjugate of 4, and this is n x conjugate of 5. Okay, n x conjugate of 6, and n x conjugate of 7. Okay, actually we require what? X of n. We require x of n. But so here we got the sequence that is equal to n x conjugate of n, and the sequence is obtained 8, 8, 8, 8, again 8, all are 8s. Okay, so we need x of n. So for that, what should we do? So we need x of n. For that, what should we do here? We should apply conjugate for this x of n sequence, and then it is divided by 1 by n. So 1 by n, 1 by n, and we apply conjugate of the sequence. So 8, 8, 8, 8 conjugate. So so here in this problem, there is no complex terms are there. Only it is consisting of real terms only. So the x of n sequence. So the x of sequence is 1 by 8. So the after performing conjugate for the sequence, so 8, 8, 8, 8 only. So the final answer is after dividing with this one, and the x of n sequence is obtained 1, 1, 1, 1, 1, 1, 1, 1. Okay, so this is our x of n sequence. So like this way, we are going to perform IDFT, inverse discrete Fourier transform, by using destination in time algorithm. The same approach, if you are following the IDFT, you can perform IDFT computation by using destination in frequency algorithm also. Okay, thank you.